Pacific Palisades, Los Angeles, January 7, 2025, 10:30 in the morning. A small fire is reported near a residential neighborhood in the mountains north of the Pacific Palisades, around 10 acres. The kind of call that California firefighters handle hundreds of times a year. The winds that morning are already extreme. A high-pressure system over the Great Basin has created a steep pressure gradient across Southern California, and the Santa Ana winds, funneling through the mountain passes and canyons, are gusting above 80 miles per hour. By the time the fire reaches the ridge above Pacific Palisades, it is moving faster than any ground crew can respond to. At the same time, in Altadena, at the foothills of the San Gabriel Mountains to the northeast, the Eaton fire ignites. By 6:17 p.m., all firefighting aircraft in the county are grounded because of the wind. Within hours, both fires are moving through neighborhoods at speeds that residents cannot outrun. Embers are being thrown miles ahead of the main fire fronts, igniting spot fires in communities that had not yet received evacuation orders. Canyons that channeled the wind into natural blowtorches are turning decades of accumulated vegetation into walls of fire, moving at the speed of the wind pushing them. By the time both fires were fully contained on January 31, the numbers were staggering. 31 people killed across all the fires that week. More than 180,000 residents forced to evacuate at the peak of the crisis. More than 250 homes and structures destroyed. The Palisades fire destroyed 1,837 structures across 448 acres. The Eaton fire destroyed 414 structures across 14,021 acres. The two fires together represent the costliest wildfire disaster in the history of the United States. Economic loss estimates have varied considerably. AccuWeather's initial estimate was $250 to $275 billion in total economic impact. Later, independent analyses placed the figure lower, with Moody's estimating roughly $95 billion in insured losses alone, and broader economic loss estimates ranging from $76 billion to $131 billion. Whatever the precise figure, the January 2025 fires stand as the most economically destructive wildfire event in the recorded history of the United States. And, on the day the fires ignited, January 7, 2025, the soil moisture in Southern California was in the bottom 2% of all historical records for that date. That number, bottom 2%, deserves to stay in your mind as this video continues, because it is not an anomaly. It is not a once-in-a-generation coincidence. It is one data point in a trend that meteorologists and climate scientists have been watching develop for 60 years, that has been accelerating, and that the forecasts for the summer and fall of 2026 suggest is far from finished producing the conditions that made January 2025 possible. The January 2025 fires were not caused by a single unusual event. They were caused by a sequence of conditions, each individually familiar to California, that combined in a way that amplified every one of them to its worst-case expression. 2 years of wet winters that grew an abundance of vegetation. A summer of extreme drought that dried every living plant and cured every dead blade of grass to tinder. A decades-long trend of falling precipitation in the fall months that left the landscape entering the Santa Ana wind season with less moisture than it historically carried. And then, the winds themselves, hurricane force, funneling through canyons above neighborhoods that had no way out. The meteorologists who study this are not losing sleep because they fear another January 2025, exactly. They are losing sleep because every one of the conditions that produced January 2025 is measurably worsening. And the season that California is heading into, as this video is being recorded, sits on top of a spring that collapsed the Sierra Nevada snowpack from 75 to 80% of normal on May 1 to just 20 to 30% by the end of May. A decline that took 4 weeks. The previous fire was destructive. What is being forecast for what comes next has prompted the language of terrifying from the people who know this system best. This video is about 3 things. The first is what actually caused the January 2025 Los Angeles fires at the level of specific meteorological mechanisms, not just drought and wind, but the precise sequence of conditions, the hydroclimate whiplash, the 60-year trend in California's precipitation timing, and the documented shift in the overlap between dry conditions and the Santa Ana wind season that made the fires as catastrophic as they were. The second is what the 2026 forecast actually says, what specific conditions are building, and why meteorologists and Wildfire characterize the risk as above normal through summer and fall. The third is the structural change that sits underneath both. A documented, multi-decade shift in California's seasonal moisture patterns that is extending the fire season into the months when the Santa Ana winds are strongest, creating an overlap that was historically rare and is now becoming regular. By the end of this video, you will understand why the January 2025 fires were not simply a worst-case year, but a manifestation of a structural change in California's climate that is still ongoing. You will understand what hydroclimate whiplash is, and why it specifically creates the conditions for the most destructive fires. You will understand what the 2026 forecast says and what specific conditions underlie it. And you will understand the mechanism that meteorologists describe when they say the fire season in California is no longer confined to summer and fall. What is hydroclimate whiplash, and how did 2 years of wet winters directly cause the January 2025 fires to be as destructive as they were? What exactly is a Santa Ana wind event? And what created the specific meteorological setup that produced 100-mile-per-hour gusts through communities in Los Angeles in January 2025? Why does it matter that the wet season in California has started nearly a month later than it did 60 years ago? And how does this interact with the timing of the Santa Ana wind season? Does the 2026 wildfire forecast for California actually say, and what specific conditions are driving the above-normal risk assessment? And what is the mechanism that connects the changes in California's climate to what meteorologists describe as an extended fire season? And why does the extension specifically into winter months matter more than an extension into summer months? This is not a video claiming California is about to have a fire that is definitely worse than January. Event: fires require ignition, weather is variable, the conditions being described create elevated risk, not predetermined outcomes. This is also not a video that treats January 2025 as a one-time extreme that will not repeat. The meteorological analysis of what caused those fires shows that the conditions that enabled them are structural, driven by multi-decade trends in precipitation timing, temperature, and the seasonal overlap of drought and wind, not by a single unusual weather event. The honest version of this story is that California is at the beginning of a transition in its fire regime. That the January 2025 fires were a demonstration of what that transition looks like at its worst, and that the summer and fall of 2026 are approaching with conditions that are, by the specific metrics that matter for wildfire risk, worse than those that preceded January 2025 in several respects. Before we continue, if the kind of science that explains why a meteorological disaster happens, rather than just describing that it happened, is what you come to Galaxy Pulse for. Subscribe. Now, back to California, and to the specific sequence of conditions that turned a small fire in Pacific Palisades into the costliest wildfire disaster in U.S. history. How the January 2025 fires happened, and what is building for 2026. California has always had wildfires. The fire ecology of the Mediterranean climate that characterizes most of the state, warm dry summers, cool wet winters, is a fire-adapted ecology. The chaparral shrublands of Southern California, the foothill woodland the grasslands of the Central Valley, all evolved in a fire environment. Indigenous communities managed fire as a landscape tool for thousands of years. European settlement interrupted those practices and allowed fuel to accumulate, creating conditions for larger and more severe fires than the historical landscape experienced. The combination of fire-adapted vegetation, dry summers, and the Santa Ana winds of fall and early winter has made Southern California one of the most fire-prone landscapes of North America for a very long time. This is not new. What is new is the specific way these factors are interacting with a changing background climate. To understand the January 2025 fires, it helps to first understand the geography of the problem. The mountains north and east of Los Angeles, the Santa Monica Mountains, the Transverse Ranges, the San Gabriel Mountains, form a topographic barrier between the coastal communities and the interior desert plateaus. These mountains are deeply incised with canyons that run roughly north-south, channeling air flowing from the desert interior toward the coast. When atmospheric conditions create high pressure over the Great Basin to the northeast and low pressure over the Pacific to the west, air flows from high pressure toward low pressure, from the desert toward the coast. The mountain canyons amplify this flow dramatically. What might be a 30-mile-per-hour regional wind becomes a 100-mile-per-hour canyon blast when it is compressed through a narrow pass. The communities that have grown up in and around Los Angeles over the past century were built in and among these canyons, on hillsides covered with chaparral, dense, highly flammable shrubland that has evolved over millions of years in exactly this fire-y environment. The chaparral burns, the rain comes, the chaparral regrows. This is its ecological cycle. The problem is not that chaparral exists in these hills. The problem is that millions of homes now exist there too. To understand the January 2025 fires, you need to understand three things in sequence. The first is what hydroclimate whiplash is and how it operates. Hydroclimate whiplash is the term scientists use to describe the increasingly common pattern in which California receives exceptionally high rainfall in one period, and then experiences exceptionally intense drought in the following period. The rains of 2022-2023 and 2023-2024 were atmospheric river events, streams of moisture-laden air flowing from the tropical Pacific that delivered exceptional precipitation across Southern California over 2 consecutive winters. These rains produced extraordinary vegetation growth. By summer 2024, the landscape surrounding Los Angeles, measured by satellite vegetation indices, had more healthy and abundant vegetation than the historical average for that period. This is the first half of the whiplash. The wet phase grows fuel. The second half is the dry phase. Summer 2024 was hot and dry in Southern California. The abundant vegetation that had grown in the wet winters dried progressively through the summer. By fall 2024, what had been living, green vegetation was dead, dry, and ready to burn. The soil moisture on January 7, 2025 was in the bottom 2% of historical records for that date. That measurement reflects not just a dry spell in the weeks before the fires, but the cumulative drying of the landscape through a summer of drought following 2 winters of unusual growth. The second thing to understand is what Santa Ana winds are, and how the specific meteorological setup of early January 2025 produced the extreme event that it did. Santa Ana winds are katabatic winds, downslope winds created when cool, dense air from the interior deserts and high plateaus is funneled through the mountain passes and canyons of the transverse ranges toward the Southern California coast. As this air descends, it compresses and warms, and as it moves through the narrow mountain passes, the topography amplifies its speed. In a strong Santa Ana event, wind gusts through these canyons can exceed 80 or 90 miles per hour. In the most extreme events, gusts can exceed 100 miles per hour. The January 2025 event was among the most extreme on record. A strong high-pressure system over the Great Basin created a steep pressure gradient across Southern California, driving the offshore flow with unusual intensity. Wind gusts reached 100 miles per hour at the Mount Lukens Truck Trail in the eastern San Gabriel Mountains. The third thing to understand is the fire behavior that resulted from the combination of these two factors. When extreme wind moves over a landscape with extremely low fuel moisture, the fire behavior that results is qualitatively different from what firefighters encounter in a normal fire event. The fire's rate of spread is proportional to wind speed. At 80 to 100 miles per hour, a fire front can move faster than any available ground resource can reposition to intercept it. Embers are carried miles ahead of the main fire front by the wind, creating spot fires in communities that have not yet received evacuation orders. Firebrand transport, the technical term for ember showers, can ignite homes and structures far from the leading edge of the fire, making the fire perimeter effectively irrelevant as a containment line. This is what happened in Pacific Palisades and Altadena in January 2025. Not a fire that spread from the ignition point outward in a predictable pattern, but a fire that threw embers into communities, igniting dozens of spot fires simultaneously over a WID-E area, while the main fire continued to advance on the wind. 20% of fire hydrants in the more elevated parts of Pacific Palisades ran out of water during the firefighting effort, not because of a water system failure in the conventional sense, but because the demand from a fire of this intensity and speed exceeded the capacity of a system that had been designed for a different fire regime. Under historical California fire patterns, the worst fire conditions occurred in late summer and early fall, from August through October. The combination of dry fuels after the summer's heat and the beginning of the Santa Ana wind season in October and November was the historically most dangerous period. December, January, and February were relatively lower risk, because the fall rains had usually begun to wet the landscape before the peak of the Santa Ana wind season. That historical pattern is changing. NOAA climate analysis of the January 2025 fires identified a 60-year trend in California's precipitation timing. Over the past 6 decades, the wet season has started nearly a month later than it historically did. Rain that used to arrive in October and November now arrives in November and December, or later. This delay means that the landscape is entering the Santa Ana wind season, which peaks in December and January, with less accumulated moisture than it historically carried. The World Weather Attribution Team, analyzing the specific meteorological conditions around the January 2025 fires, found that in a pre-industrial climate, extreme drought conditions rarely overlapped with the peak Santa Ana wind season. The two phenomena, dry conditions and strong offshore winds, had historically been offset from each other in timing by enough that their overlap was rare. That offset is shrinking. Research published in environmental research letters found that climate change has made the overlap of hot and dry conditions with the offshore wind season more likely. The likelihood of the conditions that produced January 2025 has increased by 8 to 31% compared to a pre-industrial climate. John Abatsoglu, one of the leading researchers on California's fire climatology, put it directly in a NOAA analysis. If there are longer windows where fuels remain dry, there can be more opportunities for strong Santa Ana winds to overlap. The wet season delay is the structural change. The Santa Ana wind season has not shifted much. What has shifted is when the rains come. And every year that the rains come later, the period during which dry fuels and strong winds overlap gets longer. The specific causal chain that produced the January 2025 fires is worth tracing in detail, because the same chain is the framework for understanding what the 2026 forecast is actually saying. Step 1. Atmospheric rivers in 2022-2023 and 2023-2024 delivered above average rainfall to Southern California over 2 consecutive wet seasons. This rainfall grew an unusually abundant crop of vegetation, grasses, shrubs, and chaparral, across the hills and canyons of the Los Angeles Basin and the surrounding mountains. Satellite measurements of the Normalized Difference Vegetation Index showed that by summer 2024, vegetation in both Pacific Palisades and Altadena was denser and healthier than the historical average. Step 2. Summer 2024 was hot and dry. The abundant vegetation dried. Through July, August, September, October, and into the fall, the grasses cured, the shrubs dried, and the dead fuel moisture. The technical measure of how much water is in the dead plant material that forms the primary fire fuel fell to critically low levels. Step 3. The fall rains did not arrive on their historical schedule. The wet season delay meant that the October and November precipitation that would historically have begun to wet the landscape either did not arrive or arrived in insufficient quantities. The driest 9-month period on record for Southern California had preceded the fires. The bottom -2% soil moisture measurement on January 7 is the direct consequence of this combination of drought and wet season delay. Step 4. A high-pressure system over the Great Basin in early January created the meteorological setup for a severe Santa Ana wind event. The pressure gradient drove offshore flow through the mountain passes at extreme speeds. Step 5. The fires ignited, in at least one case potentially from embers of an earlier fire that had not been fully extinguished, with power line contact under investigation as a possible cause for others. The combination of extreme winds and extreme fuel dryness produced fire behavior that overwhelmed firefighting capabilities and destroyed communities faster than evacuation could be organized and completed. This 5-step causal chain has no single point of failure. Remove any one step and the disaster is smaller, but every step was present simultaneously, in its worst-case expression. The ECMOF analysis, using the Sparky fuel model that monitors vegetation state from weather data and satellite observations, confirmed this causal sequence retrospectively. The model showed both the exceptional vegetation growth through 2024 and the ional drying that preceded the January 2025 ignitions. For the first time, a major fire weather forecasting institution had captured in real-time model output the complete buildup to a major wildfire disaster. The Sparky model, seasonally predictive and rapidly keyed to fire danger. is specifically designed to address the hydroclimate whiplash problem by tracking how vegetation state changes in response to the cumulative history of weather, not just current conditions. Traditional fire danger indices look at current temperature, humidity, and wind to estimate fire spread potential. But they do not capture the legacy of wet conditions that grew the fuel in the first place, or the full history of drying that cured it. Sparky integrates the vegetation state, how much fuel has grown, how dry it currently is, as a function of weather going back months. This is the specific innovation that allowed it to capture both the fuel growth from the 2022-2024 wet winters and the curing from the 2024 summer drought. The January 2025 fires were, in retrospect, visible in the Sparky model output. Not the ignitions, nothing can predict where and when a spark will start a fire, but the fuel state that would make any ignition catastrophic. That is the most accurate description of what scientific fire prediction can currently do. Identify when the landscape is in a state where any ignition becomes a disaster. The January 2025 landscape was in that state. That this causal sequence is not a one-time aberration, but a template for what the combination of hydroclimate whiplash and a warming, drying California climate can produce, is the core of what meteorologists mean when they describe the 2026 outlook as something that keeps them awake. Three concepts need to be precise before the rest of the story. The first is dead fuel moisture and why it is the critical fire weather variable. Living vegetation contains moisture in its cells, which makes it harder to ignite and slower to burn. Dead vegetation, dried grasses, fallen leaves, dead branches, has no living water and burns readily when ignited. Dead fuel moisture is measured as a percentage of the dry weight of the material. At 5%, material ignites easily and burns hot. At 20%, ignition is difficult. During the January 2025 fires, dead fuel moisture in some areas around Los Angeles was below 5%. The technical fire behavior threshold, above which fire spread rates begin to moderate, is approximately 12%. The landscape was more than twice as dry as that threshold. The second is the wildland-urban interface and why it matters for fire casualties and economic loss. The wildland-urban interface is the zone where developed land, houses, businesses, roads, and infrastructure meets undeveloped natural land. In the hills and canyons of Los Angeles, this interface is extensive, with neighborhoods built directly into and among the fire-adapted chaparral. When a fire moves through this interface at extreme speeds, the structures, their wood framing, their wooden decks and fences, become fire fuel alongside the surrounding vegetation. The January 2025 fires were not wildland fires that burned near urban areas. They were fires that moved through streets, destroyed addresses, and killed people in their cars. The wildland-urban interface problem is not primarily a fire management problem. It is a land use problem that has been built into the landscape over decades and cannot be rapidly undone. The third is why a wetter winter is not necessarily protective against the next fire season. This is the counterintuitive insight at the heart of hydroclimate whiplash. More rain in winter grows more vegetation. More vegetation, when it dries in summer and fall, means more fuel. A wet winter, followed by a dry summer and fall, can leave the landscape with more fuel, more broadly distributed, than a consistently dry climate would. The protection that the winter rain provides lasts only until the vegetation it grew has dried. And in a warming climate, the drying happens faster. This is why the spring 2026 storms that temporarily boosted vegetation growth across California are not unambiguously good news. A coup, weather meteorologist Brandon Buckingham noted explicitly that the rainfall temporarily boosted vegetation growth, which could later become additional wildfire fuel as conditions turn hotter and drier. The vegetation grown by spring 2026 rains is currently green. By July and August, it will be dry. Here is why the 2026 fire season is specifically concerning in ways that go beyond the ordinary year-to-year variation in fire risk. In spring 2026, record-breaking heat came to California early. The heat wave rapidly melted the Sierra Nevada snowpack. On May 1, the North Sierra snowpack was at 75 to 80% of normal. By the end of May, it had fallen to 20 to 30%. This is not a gradual decline. It is a collapse over 4 weeks. By April 1, before the May heat wave fully accelerated the melt, the statewide snowpack was already at 18% of average, TH's second lowest on record since monitoring began in the 1980s. The snowpack that would have been providing slow, sustained summer moisture to the mountains and their downstream watersheds through July and August was largely gone by June. By August, the high-elevation forests and meadows that would historically still have some residual snowmelt moisture will instead have been dry since early summer. The coastal marine layer, the fog and low clouds that moderate temperatures and provide coastal moisture in Southern California, is showing signs of weakening, particularly in Southern California. Weather meteorologist Brandon Buckingham noted that very warm Pacific water may be limiting the marine layer, potentially raising fire risk in coastal areas sooner than usual and in areas that historically had significant natural protection from fire weather. Southern California is entering the 2026 fire season with persistent drought, high grass fuel loads from spring growth now beginning to dry, and a weakening coastal moisture buffer. Fire, official fire potential outlook, identifies these 3 factors explicitly as the drivers of above-normal large fire activity expected by July and August across both Northern and Southern California. Weather's 2026 National Forecast projects 5 to 8 million acres to burn nationally, with California specifically projected at 500,000 to 750,000 acres. The forecast notes that while the total number of fires may be lower than in some previous years, fires that do occur are likely to spread faster, grow larger, and become more destructive. Fewer fires, more acres burned, is a specific pattern that reflects a fire environment in which extreme conditions, when they occur, produce rapid and large growth. The season has not yet peaked. Peak fire risk in California typically occurs in late summer and fall, when fuels are driest and Santa Ana wind events begin. This snowpack collapse is now creating the conditions that will define what the fuel moisture looks like when those winds arrive. The 2026 forecast is above normal, driven by measurable and specific conditions: drought, snowpack collapse, marine layer weakening, and the grass fuel load left by spring rains that are now drying. These are not models projecting decades into the future. They are current observations about the state of the landscape right now and what it will look like in 3 to 4 months. But, underneath, the 2026 forecast is a longer-term pattern that is more significant than any single season's conditions. A pattern in California's precipitation timing, documented over 60 years, that is extending the fire season specifically into the months when the most extreme wind events occur. A pattern in hydroclimate volatility that makes the wet-dry swings that produced January 2025 conditions more likely with every degree of warming, and a pattern in the development of the wildland-urban interface that has placed millions of people in exactly the landscape where these conditions produce the worst consequences. Understanding why the structural trend is more alarming than any single year's forecast requires understanding what the 60-year precipitation timing data actually shows, and what it implies for the future overlap of California's fire risk and its most dangerous wind season. The structural change and what comes next. The single most important meteorological fact about California's changing fire risk is one that receives almost no coverage in popular discussions of the wildfire problem. The wet season is starting later. Over the past 60 years, as documented by NOAA climate scientists analyzing long-term precipitation records across California, the onset of meaningful fall precipitation has been delayed by approximately 3 to 4 weeks compared to its historical Tim-ing. Rain that used to reliably arrive in October and November now typically arrives in November and December, if it arrives at all before January. This might seem like a minor shift, a few weeks, but the specific consequence for fire risk is severe, and it operates through a precise physical mechanism. To understand why the timing matters more than the total amount, consider what precipitation does for fire risk. It is not the total winter rainfall that determines whether the landscape will burn in December. It is whether any rain has fallen by December. A landscape that received 30 inches of rain in February and March may be as fire-prone in November as a landscape that received no rain at all, because the November fire risk depends on whether the landscape has received fall rain, not on whether it received winter rain earlier. The relevant question for fire risk in November, December, and January is: has the landscape received any significant precipitation in the past 4 to 6 weeks? And, with the wet season delayed by a month, the answer to that question in November and December is increasingly no. The Santa Ana wind season in Southern California peaks in December and January. These are the months when the atmospheric circulation patterns that drive offshore, downslope winds from the Great Basin are most favorable. The strongest Santa Ana events, historically and statistically, occur in December, January, and February. The historical overlap between the end of the dry season, when fire risk is highest, and the peak Santa Ana wind season, when the most extreme fire weather events occur, was limited. The rains would usually begin to wet the landscape in October and November, before the peak of the Santa Ana wind season arrived. The worst conditions, driest fuels and strongest winds, rarely coincided. With the wet season delay, this separation is collapsing. Now the driest conditions extend into December and January, directly overlapping the peak of the Santa Ana wind season. The conditions that used to rarely coincide are increasingly coinciding. John Abatsoglu's research, cited in the NOAA analysis of the January 2025 fires, put it precisely. Longer windows where fuels remain dry mean more opportunities for strong Santa Ana winds to overlap. The January 2025 fires were not caused by an unusually severe Santa Ana event occurring at an unusual time. They were caused by an unusually severe Santa Ana event occurring at a time when, historically, the landscape would have already been receiving fall precipitation. The unusual thing was not the wind. It was that the rain had not come. The wet season delay is not reversing. The research suggests it is connected to the broader warming trend affecting California's climate, which is increasing evaporative demand and reducing fall precipitation, specifically. As long as the background warming trend continues, the delay in the wet season is expected to continue and possibly accelerate. This means the overlap between dry fuel conditions and peak Santa Ana wind events is expected to become more frequent and more severe in coming decades. The January 2025 fires are not the extreme edge of a one-time event. They are a preview of conditions are expected to become less exceptional over time. The specific phenomenon of hydroclimate whiplash, wet periods followed by intense dry periods, is not new to California. The state's Mediterranean climate has always alternated between wet winters and dry summers. What is new is the intensity and frequency of the swings. Research, published in Nature Climate Change and related journals, has documented that the magnitude of California's hydroclimate swings has been increasing in recent decades. Wet years are getting wetter. Dry years are getting drier. The transition between these states is becoming faster and more complete. The physical reason for this is straightforward. A warmer atmosphere holds more water vapor. This is basic thermodynamics, known as the Clausius-Clapeyron relation. For every degree Celsius of warming, the atmosphere can hold approximately 7% more water vapor. More water vapor means that when atmospheric rivers or other storm systems do arrive, they carry more moisture and deliver more rain. But a warmer atmosphere also evaporates moisture from the land surface more quickly during dry periods, and higher temperatures of a warming climate mean that what would have been snow in a slightly cooler atmosphere falls as rain instead, running off quickly rather than accumulating as a snowpack that releases moisture slowly over months. The wet periods become wetter because the atmosphere can hold and transport more water. The dry periods become drier because evaporative demand increases and the snowpack that moderates the transition is smaller. For fire risk, this increasing volatility has a specific implication that is different from what a simple linear drying trend would produce. A landscape that simply gets drier over time gradually loses its vegetation and becomes less productive of the fine fuels, the grasses and small shrubs, that carry the fast-moving surface fires that enter communities. But a landscape that alternates between very wet and very dry periods is continuously producing large quantities of fine fuel during the wet years and then curing all of it to tinder during the dry years. The volatility keeps the fuel supply full. This is the paradox that hydroclimate whiplash creates. Wet years, which feel like relief from drought and fire risk, are actually building the fuel for the next fire. The fire risk comes not from the dry years alone, but from the wet year followed immediately by the dry year. January 2025 was the product of 2 wet years followed by a dry year. The fuel was built. The fuel dried. The wind came. The ECMOV Sparky fuel model was specifically designed to capture this dynamic, tracking how vegetation state changes in response to weather over time and reflecting the wet-dry alternation in its fuel moisture estimates. The analysis of the January 2025 fires confirmed that the model had captured the full whiplash sequence in its pre-fire fuel moisture estimates. The exceptional vegetation growth through 2024 and the exceptional drying that followed. What the 2026 season presents is a partial replay of this pattern. Spring 2026 storms temporarily boosted vegetation growth. That new vegetation is now entering the drying phase of a summer that is projected to be warm and dry. The fuel being built by the spring rains will be cured and ready by July and August. The meteorological conditions that produce dangerous fire weather in California are worsening. The physical fire risk, measured in terms of fuel moisture, wind frequency and intensity, and the seasonal overlap of dangerous conditions, is higher than it was 60 years ago. Both of these statements are supported by the available evidence. But the total risk to human life and economic value is not just a product of the meteorological conditions. It is also a product of what has been built in the landscape where those conditions occur. The wildland-urban interface in California has expanded dramatically over the past half-century. Millions of people live in communities built into the hills and canyons that are most exposed to fire, weather. The expansion of development into these areas has been driven by housing demand, by the desirability of natural settings close to major urban areas, and by a planning framework that historically did not account adequately for the changing fire regime. The January 2025 fires demonstrated what this expansion means in a worst-case fire scenario. Communities in Pacific Palisades and Altadena were built into deeply fire-adapted landscapes, connected to them by roads, without the water infrastructure capacity to fight fires of the speed and intensity that the January 2025 conditions produced. The 20% of fire hydrants that ran dry in the more elevated areas of Pacific Palisades did not run dry because of a water system failure in the conventional sense. They ran dry because the demand from a fire of this intensity and speed exceeded the capacity of a system designed for a different fire regime. The rebuilding that is underway in these areas following January 2025, and the broader policy discussions about where and how to rebuild, is occurring against the background of the forecast changes described in this video. The weather conditions that said the January 2025 fires are not one-time conditions. They are increasingly likely to recur. The question of whether communities should be rebuilt in exactly the same locations, with the same relationship to the wildland-urban interface, is a policy question whose answer will be shaped by how honestly the changing fire regime is communicated and understood. There are three distinct frames for understanding what the 2026 fire season forecast means. The first is the immediate forecast frame. California is entering the 2026 summer with above-normal fire conditions, drought, collapsed snowpack, high grass fuel loads, weakening marine layer, warm Pacific waters. OKU weather projects 500 to 750 000 AC res burned in California in 2026. CAL Fire official assessment forecasts above normal large fire activity by July and August in both Northern and Southern California. This is a real and specific near-term elevated risk. The second is the structural change frame. The immediate 2026 forecast is bad in part because of conditions that have been building over years and decades. The wet season delay, the increasing hydroclimate volatility, the development of the wildland-urban interface, and the warming temperatures that increase evaporative demand and dry out fuels more quickly are all structural trends rather than single-year anomalies. The 2026 forecast is elevated above normal because the background against which normal is defined has itself shifted. The third, and most significant, is the regime shift frame. The January 2025 fires represented a qualitative change in what a California wildfire disaster can look like. Not just more acres burned than usual. A fire regime in which extreme fire events can occur in January, in urban areas, with wind speeds and fire spread rates that overwhelm the infrastructure and response systems that were built for a different kind of fire. The overlap of peak Santa Ana wind conditions with maximum fuel dryness, which was historically rare and is becoming common, is a regime shift. And regime shifts, by definition, make past experience a less reliable guide to future conditions. The meteorologists and fire scientists who use the word terrifying are not describing the 2026 season alone. They are describing the trajectory, the direction that the underlying conditions are moving, and the growing likelihood that events like January 2025 will occur not once in a generation but once in a decade or more frequently. That is what keeps them awake. Not any single forecast. the direction of travel of the physical conditions that produce the worst outcomes. There is one more dimension of the January 2025 fires worth understanding, because it connects the meteorological story to a broader question about how the changing fire regime is being absorbed by the institutions that manage risk in California. Before the January 2025 fires, the California insurance market for wildfire risk was already in crisis. Multiple major insurers had withdrawn from California's homeowners insurance market in 2023 and 2024, citing the increasing frequency and severity of wildfire claims and the state's regulatory structure that limited how quickly rates could be adjusted to reflect current risk. The California Fair Plan, the state's insurer of last resort, had seen its policy count more than double as private insurers exit ed. Policyholders in fire-prone areas were increasingly unable to obtain coverage at any price from private insurers, pushing them to the Fair Plan, which itself lacks the reserves to pay claims from a major disaster. The January 2025 fires landed in the middle of this already stressed market. Initial estimates from ACU weather put total economic losses at between 50 to 75 billion, a figure that reflected property damage, business interruption, long-term economic effects, and rebuilding costs across the affected communities. Later, independent analyses by firms including Moody's produced lower but still enormous figures for insured losses alone, with Britannica citing estimates ranging from 76 billion to 131 billion. The difference between these figures partly reflects different scopes of measurement, and partly reflects the genuine uncertainty in estimating long-term economic effects of a disaster of this scale. What is not uncertain is that the January 2025 fires will accelerate the ongoing restructuring of California's homeowners insurance market, and that the communities being rebuilt in Pacific Palisades and Altadena face a fundamentally different insurance environment than they faced before. The structural change in California's fire regime, the trend toward more frequent and more severe fire events, is not just a meteorological fact. It is a financial fact, being priced by the insurance industry in ways that are affecting where and whether people can afford to live in California's wildland-urban interface. This is the larger context in which the 2026 fire season forecast sits. Not just a forecast of fire risk for one summer, but one more data point in a structural change that is reshaping the economics, the land use patterns, and the policy options of one of the most populous states in the United States. Let's come back to where we started. January 7, 2025. Soil moisture in the bottom 2% of historical records. Vegetation more abundant than normal because of 2 wet winters. Dead fuel moisture below 5% in parts of Los Angeles. Santa Ana winds gusting to 100 miles per hour. Fires moving faster than evacuation could be organized. 31 people killed. More than 250 structures destroyed across 37,000 acres in the 2 major fires alone. Economic damage in the tens to hundreds of billions of dollars, the precise figure disputed, but the scale of the disaster not. This was not a random disaster. It was a specific meteorological sequence, each step of which is understood, each step of which is driven by measurable and documented physical conditions, and each step of which is connected to structural changes in California's climate that have been building for 60 years and are continuing to build. The 2026 fire season is approaching with the snowpack at 20 to 30% of normal after a collapse that happened in a single month of spring heat. With drought conditions established across the northern and eastern Sierra, with high grass fuel loads in Outhern, California, with a weakening coastal marine layer, with cool weather projecting 500,000 to 750,000 acres burned in California and above normal large fire activity by July and August per Cal Fire own forecast. The previous fire was destructive. What is being forecast for what comes next has prompted the language of terrifying from the people who study this most carefully. Coverage of California wildfires falls into a consistent pattern that fails to communicate the specific scientific content most relevant to understanding the risk. The dominant framing is the event frame. A fire started, it grew large, it destroyed homes, it was contained. This framing communicates what happened, but not why it happened at the scale it did, and not why the conditions that enabled it are structural rather than accidental. The secondary framing is the blame frame: poor forest management, inadequate water infrastructure, utility equipment failure, housing policy. Each of these factors plays a real role in fire risk. None of them is the fundamental driver of why the January 2025 conditions were as extreme as they were. Santa Ana winds of 100 miles per hour would have challenged any realistically achievable fire management or water infrastructure. The fires did not become catastrophic primarily because of management failures. THI became catastrophic because the meteorological conditions produced fire behavior at a scale and speed that no management system currently in existence was designed to contain. Here are the specific things that popular coverage has consistently missed. The wet season delay. The 60-year trend in California's precipitation timing. The delayed onset of fall and early winter rains by approximately a month is the single most important structural change in California's fire risk. It is essentially invisibly in popular coverage of California wildfires, which focuses on drought conditions in absolute terms, rather than on the seasonal timing of precipitation relative to the Santa Ana wind season. The whiplash mechanism. The specific causal chain by which wet winters produce fire risk, by growing fuel that then dries, is counterintuitive and rarely explained. Most coverage of wet winters treats them as reducing fire risk, rather than as building future fire fuel. The Sparky model analysis of the January 2025 fires demonstrated this mechanism in quantitative terms for the first time. It almost never appeared in popular coverage of the fires. The dead fuel moisture numbers. Dead fuel moisture is the single most important variable for predicting fire spread rates and fire behavior intensity. The -5% dead fuel moisture in parts of Los Angeles on January 7, 2025, is the number that explains why those fires spread as fast as they did. It is almost never mentioned in popular accounts of the fires, which describe drought conditions in general terms without the specific technical measure. The 2026 snowpack collapse. The collapse of the North Sierra snowpack from 75–80% of normal to 20–30% in a single month during spring 2026, with the statewide snowpack at 18% of normal by April 1. The second worst on record is 10F, the most consequential pieces of fire season information available as this video is being recorded. It is not widely covered outside of specialist fire and agricultural communities. And the regime shift framing. The difference between "this was an extreme year" and "this is the new normal," or close to it, is the most important framing question for anyone living in or around the California wildland-urban interface. It is rarely addressed directly in popular coverage, which tends to treat each fire season as a new and separate event, rather than as a data point in a changing trend. The most significant pieces of current data for the 2026 fire season outlook are the snowpack collapse, the drought development, and the CAL fire seasonal assessment. The spring 2026 snowpack situation is stark. Record-breaking heat melted the Sierra Nevada snowpack far faster than normal. North Sierra snowpack fell from 75 to 80% of normal on May 1 to 20 to 30% by the end of May. This collapse is significant for multiple reasons. Snowpack provides a slow, steady release of moisture into California's watersheds through the summer, supporting soil moisture and live fuel moisture at higher elevations through June and July. When the snowpack collapses in May rather than melting gradually through June and July, this moisture source disappears 2 months earlier than it historically would. By August, the high-elevation forests and meadows that would historically still have some residual snowmelt moisture will instead have been dry since June. CAL fire, current fire, potential outlook for California identifies above normal large fire activity as expected by July and August in both Northern and Southern California. For Northern California, the primary drivers are the rapid snowpack loss, below normal spring rainfall, and a heat wave at the end of May, with approximately 400 lightning strikes. For Southern California, the drivers are persistent drought, high grass loads from spring growth now beginning to dry, and weakening coastal marine layers. The lightning number from Northern California is specifically significant. Lightning-caused fires, unlike human-caused ignitions, are essentially impossible to prevent. When lightning strikes dry terrain with low fuel moisture, fires start that no amount of preparedness or management can anticipate and pre-position resources for. The May 2026 lightning events in Northern California, even at below average frequency, have already contributed to above normal fire activity in May given how dry the fuels are. AccuWeather's Brandon Buckingham noted a specific concern about the coastal areas of Southern California. Very warm Pacific water may limit the marine layer. The marine layer, the blanket of cool, moist marine air that typically moderates temperatures and maintains some surface moisture along the Southern California coast and nearby inland areas, is a natural fire buffer. In years when the Pacific water temperatures are high, the temperature differential that drives marine layer formation is reduced, and the layer does not form as reliably, penetrate as far inland, or persist as long into the morning as it does in cooler ocean years. The coastal fire buffer weakens. CAL fire noted in its seasonal outlook that wildfire activity is already trending above normal in both regions in early 2026, with Northern California seeing a sharp rise in daily fires during May, including notable grassland incidents. The implications of the structural changes in California's fire regime extend beyond any single fire season, including 2026. For fire management, the extension of the fire season into December and January, and the increasing likelihood of fire events at urban interface locations, requires a rethinking of how California positions fire suppression resources. Historically, fire suppression resources were concentrated in summer and fall, when the fire season peaked. If the fire season now has a secondary peak in December and January, driven by the overlap of dry fuels and peak Santa Ana conditions. The resource deployment model needs to match that reality. CAL Fire and Los Angeles County Fire Department have been expanding their winter readiness since January 2025. But the scale of the structural change means that sustained investment in year-round positioning will be required. For building codes and land use planning, the January 2025 fires have already accelerated discussions about fire-resistant building materials, home hardening requirements, and defensible space requirements in the wildland-urban interface. California has updated its building codes in fire-prone zones multiple times in the past decade. The pace of those updates is likely to accelerate. More fundamentally, the question of whether certain areas of the wildland-urban interface should be permitted to be rebuilt or expanded, given a fire regime that is demonstrably becoming more dangerous, is a policy question that communities and governments will face increasingly. The rebuilding of Pacific Palisades and Altadena is proceeding, but the policy context for that rebuilding is different from what it was before January 7, 2025. For water infrastructure, the 20% fire hydrant failure rate in the elevated areas of Pacific Palisades during the January 2025 fires has prompted reviews of water system capacity in fire-prone areas across California. The specific challenge is that fire-resistant water capacity requirements, the volume and flow rate of water available for firefighting in extreme events, have not historically been calibrated to fires of the speed and intensity that January 2025 demonstrated. Revising those standards and retrofitting existing infrastructure in thousands of communities across the state is an expensive and long-term undertaking. For individual residents, the practical implication is straightforward in principle and difficult in execution. The conditions that produced January 2025 are not rare. They will recur. Defensible space maintenance, home hardening, and evacuation readiness. The individual actions that most reduce vulnerability in a wildfire event matter more than they did in a fire regime where the worst events were less frequent. And for the broader question of how California's population distribution will respond to the changing fire regime, the rebuilding and repopulation of Pacific Palisades and Altadena, and the continued growth of communities throughout California's wildland-urban interface, is proceeding against a background of increasing fire risk. Whether and how that trajectory changes is one of the most consequential long-term questions in California's future. Here is what the January 2025 fires, the 2026 forecast, and the structural trends underlying both of them reveal at the deepest level. For most of California's history as a state, the fire season was something that happened in the landscape, in the mountains, in the forests, in the chaparral. It was severe, sometimes catastrophic at the landscape scale, but it was largely separate from the urban environment of the major metropolitan areas. When people said wildfire season, they meant fires in places where people did not live or from which people could be evacuated in time. The fires happened at the edge of civilization, not in it. January 2025 was the moment when that separation ended. The Palisades and Eaton fires were not wildland fires that burned near urban areas. They were urban fires, fires that moved through neighborhoods, that destroyed houses on streets with names and addresses, that killed people in their cars trying to escape, that consumed communities that had existed for generations. The fire regime that produced them is not a fire regime confined to remote landscapes. It is a fire regime that reached into the densest parts of the Los Angeles metropolitan area. The physical mechanism that makes this possible, the combination of hydroclimate whiplash that builds fuel throughout the urban interface, the wet season delay that extends the dry period into the peak Santa Ana wind season, and the warming that increases evaporative demand and intensifies drought, does not respect the boundary between wildland and urban. It operates throughout the landscape. The fires follow the fuel, and the fuel is now distributed throughout the communities that were built into the fire-adapted chaparral. Understanding why this matters requires holding two facts simultaneously. The first is that the January 2025 conditions were not meteorologically unprecedented in their individual components. The Santa Ana winds, while extreme, were within the range of events that occur in Southern California in most decades. The drought was severe, but not unlike droughts that have occurred before. The vegetation growth from wet winters was unusual, but not unique. What was different was the combination and timing, the complete alignment of the five-step causal chain in its worst-case expression simultaneously, and the structural change in California's climate is making that alignment more likely. Each year that the wet season delay extends, each year that the hydroclimate swings grow larger, each year that the warming background increases evaporative demand, the probability of all five steps aligning simultaneously in January or December increases. There is a useful comparison to be made with how seismologists describe earthquake risk. No seismologist can tell you when the next major earthquake on a given fault will occur. What they can tell you is that the fault is accumulating stress, that the probability of rupture is increasing over time, and that when rupture occurs, the result will be within a certain range of magnitudes. The uncertainty is not about whether it will happen, but about when. California's changing fire regime has something of this sea character. The structural conditions, the fuel accumulated by hydroclimate whiplash, the dry season extended by wet season delay, the warming temperatures increasing evaporative demand, are accumulating. The probability of the five-step causal chain aligning is increasing. The uncertainty is not about whether conditions like January 2025 will recur, but about how often. The meteorologists and fire scientists who study this are not describing a future in which California's cities will burn in the way that science fiction imagines. They are describing a future in which the conditions that produced January 2025, conditions that were not themselves unprecedented in their individual components, but whose combination and coincidence will become less rare. A future in which the fire season in California is no longer something that happens in the landscape and occasionally approaches the urban edge. A future in which the fire season in California includes, with increasing regularity, events that happen in the city. That is what the trend lines show. That is what the structural change in the wet season timing means for the overlap with the Santa Ana wind peak. That is what the increasing intensity of hydroclimate swings means for the fuel that is built in wet years and de-dried in dry years. And that is why the people who look at these trend lines most carefully use words like terrifying when they look at what is being forecast for what comes next. Not because they are certain it will happen, because they understand why it could. And because what was once unlikely is becoming less so, with every year that the structural conditions move in the direction they are moving. There is one more layer to this story. The January 2025 fires occurred in January, in a major metropolitan area, and were driven by the Santa Ana wind phenomenon, specific to Southern California. But the conditions producing elevated fire risk are not confined to California or to the Southwest. AccuWeather's 2026 National Forecast Projects 5 to 8 million acres burned nationally, with high risk across the interior Northwest, the Rockies, Arizona, New Mexico, Utah, Nevada, Idaho, and western Montana. The same background conditions, warming temperatures, shifting precipitation patterns, and increasing hydroclimate volatility, that are changing California's fire regime are operating across the entire western United States. In some regions, the specific mechanisms are different. In others, the same whiplash pattern is producing the same fuel buildup and drying cycle. The question of how the fire risk across the western United States is changing, region by region, and what that means for the communities, the forests, and the water supplies that depend on the ecosystems being affected, is a larger story. That is a story for another time. We started with January 7, 2025. A small fire reported in the Pacific Palisades at 10:30 in the morning. By the time both the Palisades and Eaton fires were contained on January 31, 31 people were dead, more than 180,000 had been displaced at the peak of the crisis, more than 250 structures were destroyed. The Palisades fire burning 23,448 acres and destroying 1,837 structures. The Eaton fire burning 14,021 acres and destroying 9,414. And the costliest wildfire disaster in U.S. history had played out over 3 weeks. Then we traced the causes. Not the proximate causes, the ignition point, the utility equipment, the wind gusts, but the physical conditions that made the proximate causes capable of producing a catastrophic outcome rather than a manageable one. The 2 wet winters that grew abundant vegetation, measured in satellite imagery as denser and healthier than the historical average across both Pacific Palisades and Altadena. The summer 2024 drought that dried it to tinder, with dead fuel moisture below 5% in some areas on January 7, more than twice as dry as the 12% threshold above which fire spread rates begin to moderate. The 60-year trend in California's wet season timing that left the landscape in its driest, recorded state for that date when the Santa Ana winds arrived. The winds themselves, funneled through mountain passes at 100 miles per hour by the pressure gradient between the Great Basin High and the Pacific Low, and the fire behavior that resulted. Faster than evacuation, faster than sea attainment, throwing embers miles ahead of the main fire front into communities that had not yet received orders to leave. Then, we saw what 2026 is building toward. The North Sierra snowpack, collapsing from 75–80% of normal on May 1 to 20–30% by the end of May, having already been at just 18% statewide by April 1. The second worst on record since Monitory NG began, drought established across northern and eastern California. Grass fuel loads from spring rains beginning to dry across southern California. Marine layer weakening as Pacific water temperatures rise. Above normal large fire activity forecast by July and August by Wildfire for both northern and southern California, driven by the rapid snowpack loss, developing flash drought, and drying fuel conditions that together constitute a fire season building from an unusually poor starting position. And then, the structural trend underneath it all. A wet season arriving a month later than it did 60 years ago, creating an overlap between dry fuel conditions and the peak Santa Ana wind season that was historically rare and is becoming regular. A hydroclimate volatility that is increasing, making the wet-dry swings that produce January 2025 type conditions more likely with each degree of additional warming. And a warming that is increasing evaporative demand, drying out the landscape faster after rain events and extending the season of critical fire danger. The previous fire was destructive. What is coming is not certain, but the direction of the conditions is documented and clear. Whether the 2026 fire season will produce a disaster comparable in scale to January 2025 is not certain. Fire requires ignition, weather is variable. The above normal risk forecast describes elevated probability, not predetermined outcome. The specific question of whether the wet season delay, documented over 60 years, is primarily driven by anthropogenic warming or by natural multi-decadal variability, has some scientific debate. though the weight of the evidence points strongly toward a warming-driven mechanism. The World Weather Attribution Teams, finding that the likelihood of January 2025 type conditions has increased by 8 to 31% compared to a pre-industrial climate, represents the current best scientific estimate of the anthropogenic contribution. The confidence intervals around that estimate, 8 to 31%, is a wide range, reflect the inherent difficulty of attributing specific meteorological conditions to changes in the background climate. The relationship between Pacific sea surface temperatures, marine layer formation, and Southern California fire risk is an active research area. The 2026 concern about warm Pacific water weakening the marine layer has not yet been fully characterized in TRMS of its quantitative impact on fire risk. The mechanism is understood, but the magnitude of the effect in specific years is not well constrained by current models. The cause of the Eaton fire was still under investigation as of early 2026. With power line contact, a leading hypothesis. The Palisades fire's cause, potentially related to embers from a New Year's Day fire that was believed extinguished, with a criminal charge filed against a man suspected of reigniting it, illustrates how subtle the ignition component of a catastrophic fire can be, making prevention of future events difficult even when the fuel and weather conditions are well understood. The fire-conduit ions create the potential. The ignition is still often a matter of circumstance, and the policy question of how California's building codes, land use planning, and infrastructure investment should respond to the changing fire regime involves not just scientific questions but economic, political, and social ones that are actively contested and will remain so. The choice of whether to rebuild Pacific Palisades and Altadena exactly as they were, in exactly the same locations with the same building materials and the same relations hip to the wildland-urban interface, is being made now, while the research on the changing fire regime is still being assimilated into policy. First, the cause of a fire disaster is a chain, not a single link. The January 2025 fires required wet winters for fuel buildup, drought for fuel curing, wet season delay for timing, and extreme winds for spread. Remove any one link, and the disaster is smaller. Understanding all the links is understanding the risk. And communicating only some of the links, only the wind, or only the drought, or only the utility infrastructure, leaves the structural cause invisible and makes appropriate policy responses harder to design and sustain. The five-step causal chain is the unit of analysis that matters, not any individual step. Second, counterintuitive dynamics are real and important. Wet winters build fire fuel. Rain in spring creates vegetation that will become the fire fuel of late summer. The conditions that feel protective in one season are creating the risk of the next. Fire science is full of these counterintuitive dynamics, and communicating them honestly is essential for public preparedness. The 2022 and 2023 wet winters that people celebrated as ending drought were also building the fuel load that January 2025 ignite. This is not a reason to despair about rain. It is a reason to understand that the relationship between one season's weather and the next season's fire risk is not simple, and that a wet year does not guarantee a safe fire season to follow. Third, the distinction between weather and climate matters for risk communication. Any single fire season, including 2026, may turn out better or worse than forecast based on weather variability. The 2026 forecast could be wrong in either direction. A surprise of cool, wet summer weather patterns could reduce fire risk significantly. An extreme heat event, paired with a Santa Ana wind outbreak in October, could produce an event worse than anything forecast. But the structural changes in California's climate, the wet season delay, the increasing hydroclimate volatility, the warming temperatures, are not weather. They are the background against which each season's weather plays out, and they are moving in a direction that makes the worst outcomes more likely over time, regardless of what any particular season brings. Communicating this distinction clearly, elevated baseline risk, not predetermined disaster, is one of the most important and most difficult challenges in science communication about wildfire. Fourth, infrastructure designed for one fire regime will fail in a different one. The water infrastructure that ran dry in Pacific Palisades during January 2025 was not inadequate by the standards of its time. It was designed for the fire regime that existed when it was built. The fire regime has changed. The water system has not caught up. This same gap between the fire regime that existed when infrastructure was designed and the fire regime that now exists applies to building codes, road networks, evacuation systems, communication infrastructure, and emergency response protocols throughout California's wildland-urban interface. Closing that gap requires not just retrofitting existing systems, but redesigning them for the conditions that are coming rather than the conditions that existed in the past. Fifth, the boundary between wildland fire and urban fire has been crossed. January 2025 was not a fire that burned near a city, it was a fire that burned in a city. Understanding that the physical conditions producing that event are structural rather than accidental is the essential starting point for any serious response to the changing fire risk. The fire season in California has moved. It is no longer something that happens in the landscape and occasionally approaches the urban edge. January 2025 showed what it looks like when it happens in the city, and the structural conditions that produced it are moving in a direction that makes recurrence more likely. Whether the policy, planning, and public understanding of the state's fire risk moves at the same pace as the physical conditions is the most consequential unanswered question in California's response to its changing climate. The January 2025 fires were produced by conditions that were individually familiar to California, but combined in their worst-case expression, simultaneously. How much of the response to events like this should focus on the specific combination that produced this one, versus the structural trend that makes such combinations more likely over time? And given that the structural trend is documented, what would it mean to take that trend as seriously in policy decisions as individual extreme events are taken after they occur? The communities destroyed in January 2025 are being rebuilt. Given the structural changes in California's fire regime, and given that the conditions that produced January 2025 are expected to become less rare over time, what should inform decisions about where and how to rebuild, and who should have standing in those decisions? The residents who lost their homes, the insurers who must price the risk, the governments that must provide infrastructure, and the neighbors and communities who bear the downstream consequences of those choices, all have interests that do not always align. And, on the broadest level, the conditions that produced the January 2025 fires are measurably worsening. The tools to measure and understand those conditions are better than they have ever been. The ECMOV Sparky model captured the complete buildup to the disaster in its pre-fire output. The NOAA's 60-year precipitation trend data is publicly available. Firefighters potential outlooks are specific and detailed, but the policies, land use decisions, and infrastructure investments that would reduce vulnerability to those conditions are changing much more slowly. What does that gap between knowledge and action reveal about how societies respond to slowly escalating risks, and what would it take to narrow it? If this one stayed with you, let us know which part landed hardest. The specific causal chain of January 2025, from wet winters to drought to delayed rains to 100-mile-per-hour winds, the 60-year wet season delay, and what it means for the overlap with the Santa Ana wind season. The spring 2026 snowpack at 18% of normal statewide by April 1, then down to 20-30% in the north by the end of May. The realization that the structural conditions are moving in one direction, or the closing point. January 2025 was not a wildland fire that approached a city. It was a fire that burned in a city, and the conditions T-hat made it possible are becoming less rare. And if you want more of this, real Earth science and climate science told with the physical mechanisms explained, subscribe to Galaxy Pulse. We will see you in the next one. January 7, 2025. Soil moisture in the bottom 2% of historical records. Santa Ana, winds at 100 miles per hour. 2 years of wet winters that grew the fuel. A wet season that arrived a month too late to wet it before the winds came. 31 people, more than 16,000 structures. The conditions that produced all of this are measurably worsening, and the summer of 2026 is still ahead. A note on what fire prediction can and cannot do. There is a distinction in wildfire science that is worth making explicit, because it affects how the 2026 forecast and the January 2025 experience should be interpreted. Fire weather forecasting can tell you when conditions are dangerous. It can measure dead fuel moisture, monitor soil moisture, calculate fire danger indices, identify red flag warning conditions. It can, with the Sparky model and similar fuel state track-and-G systems, identify when the landscape has been primed by wet seasons and dried by drought to the point where any ignition has the potential to become catastrophic. This is what was visible in the January 2025 pre-fire modeling, not the fire itself, but T-heat conditions that made a fire catastrophic when it started. What fire weather forecasting cannot do is tell you when a fire will start, where the ignition point will be, or whether the specific Santa Ana wind event that coincides with dangerous fuel conditions will be moderate or extreme. The 5-step causal chain for January 2025 was largely visible in the data for steps 1 through 4, the fuel buildup, the drying, the wet season delay, and the atmospheric setup for a severe Santa Ana event. What could not be predicted in advance was that a specific fire would ignite at 10:30 a.m. in Pacific Palisades on January 7, 2025, from a specific source, at exactly the moment when all the other conditions were aligned in their worst-case expression. This is an important limitation to understand, because it affects what actions are possible in response to elevated fire risk. The 2026 forecast of above normal fire risk is not a forecast of a specific disaster. It is a forecast of elevated probability that when the inevitable ignitions occur, more of them will have the potential to become large and destructive than in a typical year, because the background conditions that determine fire growth potential are more extreme than typical. The response to this kind of probabilistic forecast is not to wait for the predicted disaster. It is to take actions that reduce vulnerability, clearing defensible space, hardening structures, preparing evacuation plans, ensuring water infrastructure is as capable as possible, before the specific event that will trigger the worst outcomes. Those actions matter most when taken before the fire, not after. The January 2025 fires were, in retrospect, visible in the landscape for anyone who knew what to look at. The satellite imagery of vegetation density, the drought monitor maps, the dead fuel moisture measurements, all of these told a story, in the weeks before January 7, about a landscape at critical fire danger. The gap was not in the data. The gap was in the connection between the data and the actions of the residents, the firefighting infrastructure, and the policy decisions that might have reduced the vulnerability of the communities that burned. Understanding what fire science can and cannot predict is not a reason for fatalism. It is a reason for a specific kind of readiness. Not waiting to respond to a fire that cannot be predicted, but using the tools that can predict dangerous conditions to take key preparedness actions when those conditions are building. That is the practical implication of what fire meteorology can currently offer. And, in California in June 2026, the conditions that matter are building now, before the fires that will eventually start in them.